Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 13th lecture under the course Maritime Structures offered by Department of Maritime Engineering at IIT Gandhinagar. We have been discussing the application of maritime systems for recent advancements and development for blue energy and blue economy. Wave energy harvest systems play a very important role in encapsulating power from natural resources like wave, wind and solar. Wave energy harvest systems, the design, applications, configuration and installation are complex in nature and many developing countries and advanced countries have been using these harness systems for substituting their power from fossil fuels to a very large extent. Norway is one classical example where close to about 30% of the power resources are generated from wind power. So India, being a developing country very fast in a rapid growth rate, is also focusing on wave energy harvest as one of the important segment of its future maritime development. Under this context, this lecture number 13 titled Wave Energy Harvest Systems 2, a series on the same, will be helpful to make you understand the design and development of another bio-inspired wave energy system, as you are going to see. We are now going to discuss about a new system by name bean-shaped multi-float wave energy converter. The research work is carried out under my supervision by Dr. Sricharan Vadiraju, and the credits go to him because he has been involved in the design, development, analysis and experimental studies of a new configuration which is also internationally and patented to Indian Patent Act at IIT Madras jointly. So, welcome to the lecture on wave energy harvest systems 2, where we are going to talk about floating multi-body wave energy converter. Friends, when I say floating body, let us see what is the bio form getting inspired. A starfish which has got radially spread wings with a central mass at the center maintains a complete balance on its body configuration for any wave approach angle. Okay? For any approach angle circumferentially, it maintains a body symmetry by its mass. The same approach is being used on the same plane. As you see here, it is a bio-inspired wave energy converter. So, which has got bean shape. So, this shape is like a bean, this shape is like a bean. So, it is a bean shape. So, this converter is examined for different float configurations. What you see on the screen is 4, can also have 6, can also have 8 configurations. So, the floats are placed circumferentially in pieces of 4, 6 or 8. So, the idea is like this. We have a central hub as we have it here. The central hub is connected to each float by an arm. The float is free to move in the vertical direction. As the float oscillates in vertical direction, this hinge arm will keep on fluttering and creates an angle of oscillation, and that is harnessed at the center. In addition, the center also being a floating buoy, it also heaves in the vertical direction. Even that variable buoyancy is also harnessed. So, at the center there is a power takeoff mechanical system PTO fixed to the central buoy, which harnesses and converts the wave energy from the central buoy and from the beans together. So, this is the idea what we see. Let us see how we grow with this idea and how we are able to configure this for a specific location of Indian sea state. So, the idea of the floating wave energy converter has been biomimicked from a starfish morphology to maintain a mass balance on the plane of oscillation. So, there is a central buoy indicated as CB, okay, which is having a power takeoff mechanism at the center, and the circumferential buoys are bean shaped connected to this. As these buoys keep on oscillating and at the center pivot point they keep on rotating, this motion, this oscillation is converted to this motion, which is transferred to the central buoy to harness power. Okay. So, the central buoy is anchored by a taut moved teethers and fixed to the seafloor. Okay. There are pre-tensioned teethers, to which they are connected to the seafloor. So, let us see the overall view of the modeling and analysis. Wave energy converter configuration is first configured. It is analyzed for stability, hydrodynamics, hydrostatic and natural periods are investigated. Then a preliminary design has been arrived. Based on the preliminary design, numerical and experimental have been computed, data collected for the time history and the performance evaluation is compared. Okay, that is the overall structure of what we are going to discuss on this under the course on maritime structures offered under SwayamPrabha at IIT Gandhinagar. So, friends, first let us see what are the possible geometric configurations of a float. So, one can have a straight float of effective length about, let us say, 2.4 meters, called as S1. One can also have a straight float but closed ends called as S2. So, one can have a curved shape float, open end S3, curved shape float called as bean float with closed ends S4, can also have a torus which is S5. So, one is interested to know amongst all these configurations which would give me a better harnessing advantage. Okay. So, the comparison is done preliminary and it has been found that the bean shaped configuration amongst all the 5 gives us the maximum harness possibility, published in the CRC Press book. Please have a look at these contents of the book to understand more about the comparison of the geometric results of these kind of shaped floats. So, then we also interest to get to performs comparisons on geometric and hydrostatic parameters of this at 4 float, 6 float and 8 float configuration at the same water depth, at the same weight and buoyancy, without altering any hydrodynamic characteristics. Then we wanted to compare 4, 6 and 8. One can see the natural periods with mooring in surge, surge, heave and pitch are more or less similar, because the added mass and other configurations of geometry do not change much, as you see here. Okay. And the natural periods without mooring also remains almost same, but without mooring there is a significant difference in the heave period. Okay. Because without mooring it becomes completely floating, therefore, heave degree becomes flexible. So, let us look at the hydrodynamic coefficients of this converter for 4, 6 and 8 configuration. The red one represents 4, whereas the blue one represents 8. The floor configuration, the 4 float configuration has the maximum added mass advantage, and it keeps on decreasing with increasing frequency in the heave degree, whereas the radiation damping, the 4 float configuration offers maximum and the excitation force is captured maximum with the 4 float configuration. So, in all the comparison, one can see that the 4 float configuration offers the maximum advantage in terms of its harness, published in Ocean Engineering in 2021. For more details, please refer to this paper to understand the comparison of these in different float configurations. Having learnt that 4 float configuration looks free and better, let us look at the free floating heave RAO for different configurations with and without PTO. So, when you have a power take-off mechanism, then the damping coefficient of this mechanism varied. The damping coefficient with a minimum gives me the maximum RAO free float, okay, whereas the damping with maximum gives me the the inferior ones compared to this one for increased frequency. So, when you are looking for a broad band of frequency, we can say that a 4 float configuration with minimum damping is able to give me a good free float heave RAO, which we want. Okay. Heave RAO, heave response is for the central buoy. The central buoy heave response flutters more with the circumferential bean shaped buoy, and the efficiency is likely to go high when you have this kind of configuration. So, we compared this, we found that there is a shift in the peak of these raw free float RAOs for different configurations. However, the minimum damping gives me a better harness of free float RAO for a wide range of frequency. So, these equations are generally used for power harnessing for regular waves. Average power is given by this equation. Available power in shallow water and deep water for regular waves and for irregular waves are given by this equation. So, one can easily find out what we call as wave energy flux, which is actually explained as wave power per unit wavefront. Okay. So, then once you know the wave energy flux, one can compute the total regular power intercepted by the device by multiplying this by the effective length of all the floats or effective wave front length. If you know that value, multiply that with the energy flux, wave energy flux, we get the total regular power from the units. So, for irregular wave parameters, we consider different damping ratios for the same significant wave height and zero crossing period. For zero incident angle, we compared the PTO damping for 500. One can see in this figure, let us say heave amplitude of the float F1 of 8 configuration float is presented here. Let us say the blue one is for 500 Newton second kg per second damping coefficient, whereas the red one is for 3000. So, though the red one shows the maximum hardness in terms of heave, but to achieve this we need to have a high damping energy exercised in the design. With minimum damping energy exercised, the blue one also shows relatively a closer value. Okay. So, between 500 and 3000, the trade off for the design depends upon how do you achieve this PTO damping. PTO stands for power takeoff mechanism. Power takeoff mechanism offers damping to the system. So, this table explains me how the influence of PTO will help you to harness the heave amplitude of the float for a 8 float configuration. If you look at the power spectral density function of F1 float, F1 float is the one which is facing the water. Okay. So, if there are central if there is a central buoy and 8 configuration and this is the wave direction, we call this as F1 float. Okay. This one the F1 float. So, power spectral density function shows me a very nice energy content for a lower damping, a very nice energy content for a lower damping. So, there is no necessity to have a very high PTO damping because it will not give me the higher energy content as for different bands of frequencies. Okay. We also did the total power captured by this float. We know how to compute this. The total power capture is given by this equation. If I know what is the power intercepted by the equivalent length of the effective length of the float. Okay. So, total power capture is given by this particular curve, which tells me in terms of kilowatt for experimental study and numerical comparison. So, 0.35 for 500 damping units damping, whereas for higher units damping the value is lesser. Okay. The power harness is not directly dependent on what is the damping ratio imposed on PTO. Even with the minimum damping ratio imposed by PTO, we will be able to get the maximum power. So, then we compared with 4, 6 and 8 configuration. The mean efficiency of the floats for the 4 configuration seems to be lesser than that of the 8, because you know the harness wave front is much higher for a 8 configuration compared to 4. Therefore, the mean efficiency of 8 configuration seems to be higher in percentage compared to this, whereas 4 configuration gave me a maximum of about let us say 17%, whereas 8 configuration is able to get me about 37%. Okay. I am talking about the mean efficiency of the system. So, let us look at the hydraulic power takeoff mechanism used or deployed in this system. So, friends, when the vertical buoy, which is called central buoy, moves up and down, this hinge will be able to flutter or rotate this circumferential buoys. Okay. Now, this circumferential buoy's motion is connected to the central buoy by power cables. These power cables will harness this motion into linear LMEG and connected here to harness power. So, an hydraulic PTO consists of double acting hydraulic piston, rotation from linear conversion mechanism. It has also have something called low pressure accumulator and high pressure accumulator, and hydraulic motor inertia and electric generator, which are the components of the hydraulic PTO, which is housed at the center of the central buoy. The details of the design, the electromechanical efficiency of this system are published in Renewable Energy in 2020. Readers are requested to please have more details about this by looking at this particular published paper. Having said this, let us now compare the total average power obtained for an optimum PTO damping of 200 Newton second per meter. So, this is a very interesting plot what we have for the average power absorbed by the system. When we go for average total absorbed power, variation PTO damping for a different periods for 4 configuration, wave height of 0.7 meter, one can see that as the damping PTO increases from 1000 to 5500, at about closer to 2000, all configurations at different periods gives me the maximum power. Okay. However, this varies, the shift varies with increase at marginal CTO. So, at 2000 with 4 configuration, we get the maximum harness, and that was arrived at this configuration from the study. Then that configuration was constructed, the experiment was conducted with the 4 configuration, and this is an enlarged view of the ball joint which connects the oscillator or the float with the central buoy. Okay. This is the detail of the ball joint, and this is an enlarged view of this ball joint, which is able to allow rotational motion, but no axial movement. Okay. No axial movement, but rotational motion is enabled. The design is published in this journal with more mechanical details of the design. Please have a look at this paper and try to understand how the mechanical design of this was arrived to fit into this PTO mechanism of the device. So, now your 4 configuration is contributed, is fabricated now. You can see the central buoy, you can see the floats which are now getting connected to the central buoy and put it in the wave basin and tested. This is a very typical frame, the typical frame which connects the bean shaped buoy at 1. These are counterweights provided at different locations to increase the mass and added mass of the system. Okay. So, typical buoy is connected on all the 4 sides and it is experimentally investigated. A free decay curve is obtained to find out the heave response and heave frequency response of the system. If you look at this power matrix, with increase in wave height and increase in period, we are able to get the maximum power in watt per meter for regular waves at 0.16 meter wave height and 0.2 meter wave height and 2.3 seconds wave period. You can get the maximum power is about 90 watt per meter. Okay. When you have about 0.2 meter wave height and 1.3 seconds, then the power is close to about 45 watt per meter. So, this matrix helps us to know how the power variation happens with increase in wave height, with increase in period, and what is the wave power obtained by this under regular waves. Okay. So, float cylinder arrangement used for harnessing power is shown in this with the geometric design and mechanical design allowed for this. So, capture width ratio was maintained, and one can see the total capture ratio in matrix in percentage with change in period and change in wave height. Okay. The maximum capture width ratio of 160 in percentage or 1.6 times were achieved for 1.3 seconds and 0.16 meter wave height. Okay. And a capture ratio of about, let us say, 60 was achieved for a larger segment of this higher wave period and higher wave heights. So, friends, this is a complete setup of this in wave basin at oceaning setup at IIT Madras, and one can see that from this direction waves are being passed and the central buoy is connecting all the circumferential buoys. It's made to oscillate and harness power, and the data acquisition system provided on the bridge acquires and understands the power collection, and it helps me to find out the response characteristics of this motion which were plotted and discussed. So, action and decay curve was plotted, and power spectral density function of floats for set 1 is shown. Under irregular waves, different studies were carried out, and one can see that the set 7 and set 4 were mutually agreeing to each other. Set 7 refers to numerical and set 4 refers to experimental. Okay. We are matching mutually for different floats of 1, 2, 3, 4 as you see here. So, once the F1 float is encountering the wave, it shows me the maximum response and maximum hardness, whereas F4 float is very much away from F1 diagonally opposite, which shows me the minimum. The remaining two floats shows me the intermittent values. Okay. The power matrix as we discussed was again said here. The total average power for F1, F2, F3, F4 cases are shown here, and the efficiency is plotted. One can see the efficiency is ranging from about 11% to a maximum of about 25%. One can harness about 25% for different sets conducted and different wave power measured from the device. So, friends, in the summary, let us see what we learned from this lecture and the design development. A novel multi-body floating wave energy converter with circumferential buoys, bean-shaped floats was developed. It is analyzed to understand the efficiency of harvesting wave energy in Indian, near shore and shallow to intermediate sea states. Extensive numerical investigations were carried out in frequency domain and time domain to understand the float geometry, influence of float number and power takeoff mechanism damping on the design. The parametric studies chosen on 4, 6 and 8 float configurations reveal that the bean-shaped float exhibits superior aerodynamic performance, constructive multi-body interaction and direction insensitivity for the given system. Scaled experiments were validated, and we understood that aerodynamic conversion efficiency is close to about 25% approximately for Indian sea states. The regional performance and techno-economical assessments were also carried out to prove that this is a proof of concept which can be suitable for small scale wave energy harvesting applications. Let us quickly see a video how this model was behaving experimentally. So friends, one can see the central buoy moving up and down in heave direction, circumferential buoys pitching about the connection. Together they harvest the energy which is captured and recorded using a DAQ system provided on the top. So friends, in this lecture we learnt about the wave energy harvest system design. We understood how a floating wave energy device can be configured to harness wave energy. Important parameters that govern the design are the mass ratio, the capture width ratio, the mass distribution to achieve near resonance condition harvest, then the damping optimization, and of course the overall efficiency calculation for different sea states and wave directions. So friends, these two lectures inspire you to learn and develop new wave energy harvest designs which can suit Indian sea states, and of course as a part of blue economy and energy revolution, we understand that maritime industry is also inviting applications in terms of wave energy harvest as a part of maritime sector to develop in-house as well as to have a sustainable approach towards the power utilization for different maritime structures, whether it is on ship or on coastal structures as a part of maritime sector. I request you to please go through these lectures in advance and also all the papers cited in the reference in the lectures to understand more and to learn more about these designs and developments. If you have any questions, please post us to SwayamPrabha portal, and in the discussion forum, instructors will help you to understand and answer your queries more in detail, and also you have an access to the virtual library of the textbooks cited in this course at IIT Gandhinagar library. So please have a look at these books and learn more and improve and reinforce your skilled learning through these lectures. Thank you. Namaste.